So today we're going to be solving for x in the modular equation 128 to the power of 129 equals x mod 17. Now we're going to use something called Fermat's little theorem. So we use this theorem to compute powers of integers modulo prime numbers. We use it in primality testing and public key cryptography. It simplifies the exponent. Okay. So these are the two modular equations for Fermat's little theorem. Number one, a to the power of p equals a mod p. Now for this to work, p must be prime. So as you can see, 4 isn't prime and 16 is not 2 mod 4. 5 is prime and 32 does equal 2 mod 5. Now, the second equation is a to the power of p minus 1 equals 1 mod p. So for this to work, a cannot be divisible by p. So we're going to use x mod 17 to give examples of the second equation. So 1000 to the power of 17 minus 1, which is 16 equals 1 mod 17. So this is valid because 1000 is not divisible by p, which is 17. We could use other values. We just can't use 34 or 68 because those are all divisible by 17. Okay, so p equals 17. Okay. So we can also use 7 to the power of 16 equals 1 mod 17. So basically any value to the power of 16 equals 1 mod 17 as long as x isn't divisible by 17. So for the first equation, we can do 1000 to the power of 16 equals 1000 mod 16. Maybe I should use a smaller number, but 16, p equals 16 is valid because 16 obviously isn't prime. If p equals 17, then that wouldn't work. So x to the power of 16 would equal 16 mod x. So this is Pierre de Fermat. He obviously invented Fermat's little theorem. He also has another theorem called Fermat's last theorem, and we're not going to go too deep into it, but we'll just see what it is. So Fermat's last theorem, let me highlight it. We're not going to use it to solve our problem, but it's still important. Okay, so let's just say n is the exponent. If n is more than 2, then for positive integers a, b, and c, let me just use a different color, a to the power of n plus b to the power of n cannot equal c to the power of n. So back to the problem, 128 to the power of 17 minus 1 equals 1 mod 17. So again, we're looking for x mod 17. Okay, so 16 times 8 equals 128. Okay, so this is useful because we're looking for 128 to the power of 129. So 128 is 1 away. Let me just highlight this. Okay, so okay. From this, we can deduce that 128 to the power of 16 to the power of 8 equals 128 to the power of 128. So we need to multiply this quantity by 128 one more time to achieve 128 to the power of 129. Okay, so 128 to the power of 128 would equal 1 mod 17 to the power of 8. Okay, so basically we're multiplying 1 8 times, so 128 to the power of 128 equals 1 mod 17. So we're already mostly there. We already found out what 128 to the power of 128 is. So now, okay, so I just want y'all to keep in mind that 1 mod 17 to the power of 8 is 1 to the power of 8 mod 17. Not to be confused with 8 times 1 mod 17. This would give us 8 mod 17. So multiplying by a number and using it as like a power are two different things. So what we're looking for is 128 to the power of 129, which is 128 times 128 to the power of 128. So we already know that 128 to the power of 128 equals 1 mod 17. So we need to look for what 128 equals. So 128 equals 17 times 7 plus 9, or 119 plus 9. So 128 equals 9 mod 17. So now we have that value. Let me just highlight it. We need to find this multiplied by 128 to the power of 128, which is 1 times 9 mod 17. Okay. So 128 to the power of 129 would equal 9 mod 17. So that's the answer. Thank you.